Jimmy Akin's Mysterious World is brought to you by the Star Quest Production Network and is made possible by our many generous patrons. If you'd like to support the podcast, please visit sqpn.com/give. Jimmy Akin's Mysterious World is also brought to you in part through the generous support of Aaron Vergeson Electric and Automation, making connections for life for your automation and smart home needs in North and Central Florida at aaronv.com. And by Dr. Jimmy Turner, your guide to practical leadership at drjimmyturner.com. And by rosaryarmy.com. Have more peace. Visit rosaryarmy.com and get a free all-twine knotted rosary, downloadable audio rosaries, and more. Make them, pray them, give them away at rosaryarmy.com.
Previously on Jimmy Akin's Mysterious World.
We're talking about whether the Bible teaches that we live on a young earth. For many centuries, Jews and Christians have read the Bible and thought that the world is only a few thousand years old. But after the scientific revolution began, many began to suspect that it's far, far older, billions of years old.
We need to look at these two theories from both the perspectives of faith and reason, and we need to look at the faith perspective first. The results of science are always provisional. So, if we could show from the faith perspective that God has revealed that the earth is only a few thousand years old, that would settle the matter and we could save ourselves a lot of work. We'll thus look at the evidence from the sources of faith first, and then, if it turns out they're not conclusive, we'll look at the scientific evidence from the reason perspective. Ancient historical writers sometimes grouped material in topical rather than chronological order. All this means that we need to be attentive to the fact that the biblical authors sometimes organize material in a topical way rather than a chronological way. Could those days be a literary device, meaning that they're not literal, and the biblical author is simply giving us an account of the work of the Creator that's organized by topic rather than by time? Well, here's the twist. The ancients knew just as well as we do that it's light from the sun that causes it to be day. So, what is a careful ancient reader to make of the fact that the day-night cycle was created on day one, but the sun, which makes it daytime, wasn't created until day 4? It's reasonable to take the days as a literary device. The attentive ancient reader would have realized that there wouldn't be any literal days before the creation of the sun. According to paragraph 337 of the Catechism of the Catholic Church,
God himself created the visible world in all its richness, diversity, and order. Scripture presents the work of the Creator symbolically as a succession of 6 days of divine work concluded by the rest of the seventh day.
So the Catechism concludes that Genesis depicts the work of the Creator symbolically as a succession of 6 days, meaning that the text really does tell us what the Creator did, but not in a way that gives us a literal chronology.
So, Jimmy, what is your preliminary bottom line?
My bottom line for now is that the Church has ruled that the sources of faith don't rule out the idea of an old Earth, so we'll need to turn to the scientific evidence next.
You're listening to episode 120 of Jimmy Akin's Mysterious World, where we look at mysteries from the twin perspectives of faith and reason. In this episode, we're talking about the scientific evidence concerning whether we're living on a young or an old Earth. I'm Dom Bettinelli, and joining me today is Jimmy Akin. Hi, Jimmy.
Howdy, Dom.
People debate whether we live on a young Earth that's only thousands of years old or on an old Earth that's billions of years old. This debate led the Church to examine the sources of faith, the Bible and the Church Fathers, and consider whether they required us to believe in a young Earth. The Church concluded that they don't, that it is possible to read Genesis and the rest of divine revelation in a way that allows the possibility of an old Earth and an old universe. But just because the sources of faith allow this doesn't mean that it's true. This is a matter that needs to be explored through science. So, what does the scientific evidence point to? A young Earth or an old one? And that's what we'll be talking about on this episode of Jimmy Akin's Mysterious World. So, Jimmy, we should have mentioned again, the reason we're talking about this particular topic now is through patron requests.
Yeah, if you are a patron at a certain level, we invite you to choose a topic of a particular episode. And this time we had two patrons choose very similar topics. One of them was Joel Kolb, who wanted us to evaluate radiometric dating, which is one of the ways that we test the ages of rocks. And the other was Simon Michalik, who wanted us to investigate the question of whether we are living on a young Earth. And those two questions are very intertwined. And so today we're going to be looking at what the scientific evidence has to say.
All right. So what should we say to begin today's discussion?
First, I want to note that this is the second part of a three-parter. There was so much to say on this subject that it's going to take us 3 episodes. So this is the middle act of the 3-act play. We'll have the explosive finale next time for you. And I'm not kidding when I say explosive. But I also want to follow up on what we did in Act 1 with a note about the faith perspective from last episode. As we saw, the sources of faith, such as the Bible, don't require a young Earth for the reasons we discussed. For example, the fact that the day-night cycle is created on day 1 in the Genesis narrative, and the sun, which causes the day-night cycle, was not created until day 4, is a big clue in Genesis 1 that it's giving us a topical account of the work of the Creator rather than a chronological one. So if you haven't heard that episode or you want a refresher, go back and listen to episode 119. And thus we concluded that, as the Catechism of the Catholic Church says, Scripture presents the work of the Creator symbolically as a succession of 6 days of divine work. Because the Bible isn't trying to give us chronological information about the age of the earth, we won't be appealing to theological data in this episode. We'll be looking strictly at what the scientific evidence suggests. And as part of that, we need to introduce 2 terms that regularly appear in discussions of the scientific evidence. Those terms are uniformitarianism and catastrophism, and both terms were coined back in the 1800s.
Okay, so what is, I'm going to try to say this, uniformitarianism?
The concept has been understood different ways, but for our purposes, the main version of it is basically that the Earth got into its present state by processes that extend back in time uniformly. That's why it's called uniformitarianism. It is not that strange church down the road that doesn't really believe in anything. Instead, it's about these historical processes. For example, geological processes like the movement of wind and water can cause small grains of dirt and dust to accumulate, eventually forming rocks, putting down layers of sediment, and over very long periods of time building up mountain ranges. Similarly, the same processes of wind and water can tear away small pieces of dirt and dust, leading to the gradual erosion of rocks and mountains, slowly creating flat plains or deep valleys. In the biological sphere, life forms are subject to constant low-level radiation that causes tiny mutations in their genetic code, and some of these either help or hurt their chances to survive and reproduce. Over time, those life forms that develop characteristics that help them end up outpopulating those with mutations that hurt them, and species gradually change and develop through the process of evolution. In both cases, the processes are thought, on the uniformitarian view, to be slow, and the resulting changes take place only over long stretches of time, like millions of years.
So what is catastrophism?
Catastrophism is the idea that the Earth got into its present state primarily through a series of massive catastrophic events that caused changes over a much shorter timescale. The most famous example of this discussed historically is Noah's flood, which will be the subject of another upcoming patron episode. But whether or not a catastrophist believes in Noah's flood, he would hold that big changes happen rapidly. Mountains can go up very quickly, valleys can be carved very quickly, and life forms that are around could change very quickly.
So you just said whether or not a catastrophist believes in Noah's flood. Does that mean that catastrophism isn't just a view that's been held by religious people?
Yes, in fact, both uniformitarianism and catastrophism have been held both by religious and non-religious people. So these shouldn't be seen in us versus them tribal terms. They cut across both tribes. You might get the contrary impression from some young Earth supporters because, as we'll see, their view is pretty firmly in the catastrophist camp, and they often criticize uniformitarians. However, you can be a catastrophist even if you're not a young Earth supporter or even religious. In the same way, you can be a uniformitarian, regardless of whether you're religious or not.
Are uniformitarianism and catastrophism irreconcilable viewpoints?
No, they're not. In fact, the majority view in the scientific community is that Earth's history has been significantly shaped both by catastrophic events and by slow, uniform processes that then operate between the catastrophes. The majority position in the scientific community is thus a hybrid of uniformitarianism and catastrophism. And that's important to remember because sometimes young Earth supporters will oversimplify this and portray mainstream scientists as if they have purely uniformitarian views, which they don't.
Can you give some examples of catastrophes that are accepted in mainstream science?
Sure. One of the most popular theories about how we got the moon is that about 4.5 billion years ago, the early Earth was struck by a Mars-sized body that has been named Theia. Both Earth and Theia were then smashed and recongealed into two spinning bodies, giving us the present Earth and Moon. This theory isn't accepted by all, but it is one of the most popular, really the most popular view in the scientific community about the Moon, and it obviously would have been a catastrophic event that brought about sudden change. Also, it's commonly thought that the Earth got its water oceans from repeated impacts by icy comets, and a bunch of comet impacts would definitely be catastrophic. However, there is an alternate theory that Earth already had its water when it's formed, and we'll have a link in the further resources so you can read about that. That was recently in the news. It's also popularly believed in the scientific community that about 4 billion years ago, Earth experienced a period known as the Late Heavy Bombardment, when it was repeatedly struck by a bunch of asteroids and comets, bringing even more catastrophes. In fact, the early history of the Earth is thought to have been a particularly catastrophe-prone period. But as the solar system finished forming, the number of catastrophic events began to decrease and things became more stable, allowing more uniform processes to take over. Still, catastrophes occur from time to time. 60 million years ago, on the standard scientific account, something killed the dinosaurs, ending 70% of all species and causing a massive shift in the population of life forms that were around. This may have been due to a 6-mile-wide asteroid that impacted in Mexico. That asteroid may have been part of a swarm of asteroid impacts around the same time, as we discussed in episode 88 on the Nemesis Death Star theory. It, of course, also could have been a spaceship from the future that had been hijacked by Cybermen and being unsuccessfully piloted by a boy with a badge for mathematical excellence.
Right. See recent episodes of Secrets of Doctor Who for that one.
Yeah, Earth shock. But in addition to the asteroid theory, some also think that supervolcanoes may have played a role, as we'll discuss in an upcoming episode on the death of the dinosaurs. But any way you go, it was a massive catastrophe with implications for the whole planet. So, periodic catastrophes still occur with asteroid and comet impacts, with volcanic eruptions, earthquakes, tsunamis, massive floods, and some scientists even think that we may have been hit by radiation from exploding supernovas. But these days, planet-wide catastrophes are less common. There are, though, still local catastrophes, and these can cause dramatic changes in the local areas where they occur. Contemporary science acknowledges all of this, and so it's a mistake to portray the mainstream scientific community as if they're a bunch of wooden uniformitarians who don't give a place to the idea of catastrophes in history. They're very much aware that such catastrophes occur, and that's not scientifically controversial. It's a question of when have given catastrophes occurred and what evidence does that allow us to explain.
Is there anything else we should know about uniformitarianism and catastrophism?
You'll notice that I've been talking about the two concepts in relation to geological and biological processes, like how we get mountains and why species go extinct. But these processes aren't the only ones that need to be considered, and uniformitarianism and catastrophism can operate on other levels. They're not as relevant to our discussion, but they do exist, and these terms get used for them. At the top level, there's the metaphysical level, which deals with the laws that fundamentally govern reality. One such law is the law of cause and effect. And everyone that I'm aware of is basically a uniformitarian on the metaphysical level, and they hold that the laws of metaphysics, like cause and effect, apply uniformly throughout world history. So there's never an event that just has no cause. It might have a natural or a supernatural cause, in which case it might be a miracle, but if God is its cause, it still has a cause, so the law of cause and effect holds. I'm not aware of serious metaphysical catastrophists, people who would hold that things sometimes happen for no reason whatsoever. At least I'm not aware of any in the mainstream scientific or in the Christian communities. Taking one step down from the level of metaphysics, we come to the realm of physics, which deals with a whole bunch of laws we see operating in nature. For example, physics deals with principles like the law of gravity and the speed of light and the strength of the strong and weak nuclear forces that govern radioactive decay. The mainstream scientific community is pretty strongly uniformitarian when it comes to the laws of physics. They are held either not to change over time or not to change very much. For example, you will find some physicists who say that there is evidence that the speed of light might have been slightly lower or faster in the past, but only by a tiny fraction. On the other hand, people in the young Earth community often are catastrophists when it comes to the laws of physics, and they hold that some of the laws of physics were dramatically different in the past. For example, some have held that the speed of light was very different in the past by multiple orders of magnitude. Then, so we've covered the metaphysical level and the physics level. Then if we take a step down from the laws of physics and look at geological and biological processes, you get a mix. In the mainstream scientific community, you have an acknowledgement of both uniformitarianism and catastrophism. Most of the time, rivers cut valleys slowly, but sometimes there may be a catastrophic flood or mud flow that causes a valley to be cut rapidly. Most of the time, life forms evolve very slowly, but sometimes an event happens that dramatically changes the environment in which they exist, or a really useful mutation occurs, and this causes evolution to proceed more rapidly. So according to many scientists, evolution thus involves a process known as punctuated equilibrium, in which life forms remain in relative equilibrium for long periods, but these are occasionally punctuated by rapid evolutionary changes.
Do you also get a mix of uniformitarianism and catastrophism in the young Earth community?
Sure, they acknowledge that there may be, and they would say are, catastrophic events like Noah's flood, but most of the time we see laws operating that make slow incremental changes. So you don't normally go outside one day and find there's suddenly a new mountain or a new canyon that wasn't there yesterday. The real question for both perspectives is, what's the right balance between uniformitarianism and catastrophism, and how long of a timescale do the resulting slow and rapid processes have to play out?
All right, let's look at the arguments for a short timescale and a young Earth. What case do young Earth supporters make?
The core of their case is based on their understanding of biblical passages, and specifically Genesis 1. This is the main driver of the young Earth view, and when you read their literature or listen to their lectures, you find frequent appeals to it. However, we looked at that evidence in our previous episode, and so we won't be covering all that again here. When you look at the arguments that young Earth supporters propose from a purely reason perspective, they fall into two classes. First, there are arguments they make attempting to show that the case for an old Earth or an old universe either is not convincing or not reliable. You might classify these as negative arguments because they seek to undermine the case against their view. But then second, there are arguments they make attempting to show directly that the Earth can only be a few thousand years old. You might classify these as positive arguments since they make a positive case for their position. The number of individual arguments made in young Earth literature is very large, and there's no way we could cover them all in a single episode. We would literally have to take dozens of episodes to explore them. So to narrow the field, we'll be setting aside certain kinds of arguments. We won't be looking at arguments regarding biological evolution, since we'll have future episodes on that topic. We also won't be looking at arguments concerning Noah's flood and flood geology because we already have an upcoming episode that another one of our patrons has requested on that topic. To keep the scope of our discussion at reasonable length, we'll be looking principally at two subjects. One of them is the issue of radiometric dating. And the second, which we'll get to next episode, is the problem of starlight and how light from distant stars that are apparently billions of light years away could have reached us in just a few thousand years.
If listeners want to go further with arguments for and against the young Earth, do you have any resources to recommend?
We'll have a link to the full text of a document published by Creation Ministries International called 101 Evidences for a Young Age of the Earth and the Universe, as well as a response to it by the folks from Rational Wiki. As the name of the document suggests, it contains more than 100 arguments for a young Earth, young universe point of view. Creation Ministries International was formerly known as Answers in Genesis Australia, and they're a major young Earth organization. Rational Wiki is a secular, skeptical organization that unfortunately is often insultingly dismissive of people they don't agree with. However, this link will let you see a wide selection of the young Earth arguments set side by side with responses so you can more easily evaluate them yourself. And even though I don't like Rational Wiki's style a good bit of the time, they do make a point about something I've run into in arguments being made from a young Earth perspective. Now, this is not something that happens all the time, but sometimes young Earth arguments involve a couple of fallacies known as affirming the consequent and the spotlight fallacy.
All right, what's affirming the consequent?
It's a logical fallacy that occurs when you take an if-then statement, so if then that, and you affirm the then part of the statement as a way of arguing for the if part. For example, if something is a dog, then it has 4 legs. This has 4 legs, therefore it is, or despite appearances, might be a dog. This type of reasoning can seem plausible because dogs do have 4 legs, but so do cats and chairs. And if the thing in front of you is a cat or a chair, it's wrong to argue that it might be a dog just because it has 4 legs.
All right. What about the spotlight fallacy?
This occurs when you take some particularly well-known evidence, that is, evidence that's had a spotlight shown on it, and you improperly apply what you've learned from that evidence more broadly. An example of the spotlight fallacy would be the law enforcement agents at Ruby Ridge acted really badly. Therefore, all law enforcement agents act really badly. That's not a valid inference. Ruby Ridge was a famous event where law enforcement did act badly, but there are lots of law enforcement agents who are extremely professional and act properly, and in fact, they play a vital function in our society. So you can't realize, here we got a few famous bad apples, and infer from that all apples are bad. It's a fallacy based on particular examples that have been spotlighted. With that in mind, here's what Rational Wiki notes about the list of the 101 arguments that they consider.
Many arguments on the list suffer from a specific combination of affirming the consequent with the spotlight fallacy. If the Earth is 6,000 years old, we expect X to be less than 6,000 years old. Under some circumstances, X can form in less than 6,000 years. Therefore, the Earth could be 6,000 years old. This is wrong on two levels. Firstly, an Earth that is billions of years old can be expected to have things younger than 6,000 years on it, such as you. Secondly, even if one example of X really is young, it doesn't mean all X are. The vast majority of X mentioned in the arguments can be shown to be far older than the entire young Earth timescale.
I've noted that this kind of reasoning is often present in a lot of young Earth presentations. For example, here's a clip of young Earth geologist Dr. Steve Austin, and I don't know if he has bionic parts or not, but he's describing how the Mount St. Helens eruptions in Washington state in the 1980s rapidly laid down several layers of ash and mud and also rapidly cut a canyon out of them.
This gigantic pit was here, and then into that pit came the next deposits. On June 12th, 1980, about 9 p.m. to midnight, there was a big eruption of Mount St. Helens, another big eruption. And during that 3-hour period, there were enormous pyroclastic flows, high density, very hot slurries of volcanic ash that came out of the crater. This low area in the pit collected those volcanic ash layers. And so we see behind us, about halfway up the cliff to about 3/4 of the way up the cliff, we see a 25-foot thickness of layered volcanic ash. That's the pyroclastic flow deposit from June 12, 1980. And it formed just in the 3 hours there late in the evening. And then this pit sat here with the landslide debris and the other kinds of material, the volcanic ash all around it. And then mud flow of March 19th, 1982, that came down here at 90 miles an hour. It filled in this low area, the pit, with mud. And you're seeing the residue of the mud, about 25 feet in thickness there at the top of the cliff. As the mud came into this pit, it actually filled the pit with 100-foot thickness of mud. The pit was filled, and then what happened is the mud overtopped the debris dam that was downstream of here, and then it cut a spillway over the top of that dam, which cut back through here and gouged out the bottom of this pit and released the mud downstream. And so the canyon formed in a day on March 19th, 1982, by the drainage of the mud in this big pit through the debris avalanche.
So you sit here and you look at the complexity of the geological formations, and it would be easy for someone, if we just blindfolded them, brought them down here and took the blindfold off, to look around and think, as a lot of people do, man, this is really, really old. Look at all these different layers and all of this stuff that's going on, and yet each of these layers is laid down rapidly within a day and breached within a day.
Yeah, so
that's amazing.
So although it's spread out over 2 years period, each of those individual events happens in just minutes or hours.
So we end up having a very complex geological formation here that was all done rapidly.
Yeah.
What you can validly infer from this is that when you have a volcanic eruption, you can have layers of ash and mud laid down rapidly. You can also validly infer that if you have a catastrophic mud flow, you can rapidly carve a canyon, particularly if it's cutting through loose things like layers of ash and mud. But notice how the two gentlemen seem to generalize this. Without saying it explicitly, they seem to be hinting that maybe all the layers we see in the geological formations were laid down rapidly, and maybe all the canyons we see were cut rapidly. So maybe none of the geological formations we see on Earth are more than a few thousand years old. But that wouldn't be a valid inference. It's a possibility we could consider if we knew nothing else. But if we know other things, we have to be careful. For example, we know that not all geological layers we see are made out of volcanic ash and mud. Many are made out of rock, and some are made of sedimentary rock that didn't flow out of a volcano. Now, I don't want to misrepresent Austin and say that he never acknowledges things like this, but I do find a lot of young Earth arguments either hinting or outright stating that just because we can show that a particular thing happens sometimes in a rapid fashion, that everything in the geological record should be understood in terms of things happening rapidly.
How can we try to settle the issue of what happened rapidly versus what happened slowly?
It involves a variety of factors, and some of these involve looking at the surrounding area, at the context of a particular thing. For example, if we know that volcanoes can rapidly lay down certain types of layers, is a geological formation we're looking at made of those types of layers? Is it made of lava or volcanic ash or mud or something else like sandstone? Also, is there a volcano in the area that could have produced it? Similarly, if we know that mud flows can rapidly form canyons, even granting that a violent one may be able to cut through some rock formations, do we have evidence of a violent mud flow in the area we're examining? Another big part of the answer is found by trying to directly measure the age of the geological things that we're looking at. Let's say we're looking at a rock. If the rock is young, then the processes that formed it must have been rapid, at least in the sense of being something that took place in thousands of years or less rather than millions of years or more. But if the rock is old, millions or billions of years old, then it must have been stable for a long time, and regardless of whether it was formed quickly or slowly, we've got evidence for an old Earth.
And that brings us to radiometric dating, which is a key way of trying to determine the age of a rock. But first, we'd like to take a moment to thank our patrons who make this show possible, including Jason L., Keith M., William M., Ruth M., and Andrew T. Their generous donations at sqpn.com/give make it possible for us to continue Jimmy Akin's Mysterious World and all the shows at StarQuest. You can join them by visiting sqpn.com/give. And Jimmy, do you want to take a moment now to talk a little bit about our efforts to reach financial stability for the network and continue the show?
Right. So thanks to all of the patrons that have signed up already or who have increased their pledges, we are much closer to our goal of financial stability than we were in the past. We are actually quite close to it now. And with your help, we hope to be there soon. And we have a special thing we're going to be able to do to celebrate. Faith Life Corporation, the makers of Verbum Catholic Bible software, have given us a number of packages. The specific number, Dom, is 16 packages, and they range in value from $300 all the way up to $2,000. And we're going to be giving away those to our patrons as soon as we hit our financial stability goal. We really are quite close. So just a few new patrons or just a few people increasing their monthly pledges will get us there. And once we get there, we're going to do a drawing of all of our patrons at that time. So if you're a current patron, whether you've been one for a long time or a new one, you'll be entered into that drawing. We're going to give away these 16 packages of Verbum Bible software. This is the software that I use basically every day. So it's very powerful software. There are loads of resources available, and I just use this all the time. It's essential to my work. And so I think you'll like it too. And I hope you'll either become a patron or, if you are one, consider increasing your contribution so that we can get to that financial stability point. And we're not entirely sure when we will hit it, but if we hit it before the end of September, then at the end of September, we'll do the drawing. So you have until then to become a patron. And if we haven't hit the financial stability goal by the end of September, then we'll do the drawing as soon as we do. And we're really close. We're really hopeful. Please make your contribution. Go online at sqpn.com/give. Once again, it's sqpn.com/give and become one of our monthly supporters. And thank you so much.
Thank you to all our patrons. Jimmy Akin's Mysterious World is also brought to you in part through the generous support of Aaron Ferguson Electric and Automation, and by Dr. Jimmy Turner, and by RosaryArmy.com. So, Jimmy, how does radiometric dating work?
As we covered last episode, it involves measuring the amounts of certain elements, particularly radioactive elements and the elements that they decay into. The most famous such element is carbon-14, also known as radiocarbon, and it decays into nitrogen. The rate at which a radioactive element decays is known as its half-life, which represents the amount of time it will take half of the radioactive atoms to decay into something else. In the case of carbon-14, its half-life is around 6,000 years, meaning that after 6,000 years, only half of the carbon-14 atoms will still be there, and the rest will have turned into nitrogen. After 12,000 years, only a quarter of the carbon-14 will be left, and after 18,000 years, only an eighth of it will be left, and so on. So, if you can get a good estimate of how much carbon-14 was in something originally, and you see how much it has now, you can estimate how old it is. But there are limits. In the case of carbon-14, it decays fast enough that if an object is more than about 60,000 years old, you can't use carbon-14 to date it anymore. You have to use something else. Also, carbon-14 is best used for samples from what used to be living, breathing organisms that were consuming carbon-14 from the atmosphere when they ate and breathed. Carbon-14 dating is thus good for things like wood or leather, since living things consume carbon-14 from the air at roughly a constant rate. But for things that are older than 60,000 years or that were never living, like pieces of rock, you need something else. And so scientists have used other radioactive elements, such as potassium-40, which decays into argon, uranium, which decays into lead, rubidium, which decays into strontium, and samarium, which decays into neodymium. In each of these systems of radiometric dating, the original radioactive isotope is called the parent atom, and the one it decays into is known as the daughter atom. So carbon-14 is the parent that gives birth to the daughter nitrogen. And you want to remember the terms parent and daughter because they're going to come up more in this episode and next episode. Now, in order to measure how old a sample is based on the parent and daughter atoms it contains, you need to know certain things. In a talk which we'll have a link to, Australian young Earth geologist Dr. Andrew Snelling identifies three of these things. He refers to them as assumptions, but that may not be the best term because there are ways to estimate these things, and an estimate is not the same as an assumption.
What's the first thing you need to know about a sample?
Its initial conditions. That is, you need to know something about how many parent and daughter atoms it would have contained initially. You can get an estimate of that in the case of carbon-14 because living things are constantly processing these atoms through their metabolisms. They take them in from the atmosphere when they eat or breathe, and then they either make them part of their bodies or they expel them back into the environment. As a result, the amount of carbon-14 a living thing contains at any one time is fairly constant when it's alive. You can thus estimate the amount of carbon-14 it had when it died and stopped metabolizing. So you can measure what fraction of the parent carbon-14 atoms are left to estimate the age. And as we saw last episode, helium is another key marker that's used in uranium, thorium, helium dating. You can estimate that a normal rock should have virtually no helium in it, since there is almost no helium in the atmosphere. It's 0.0005% helium. That's just 5 atoms per million atoms in the atmosphere. Also, helium is the snootiest of the noble gases, so it doesn't like mixing with anything, and it shouldn't have grabbed onto other atoms in the rock when it was formed. Thus, if you have a rock that has uranium and thorium in it and helium, Any helium atoms you find in the rock are likely daughter atoms that were produced by uranium decaying. But, however you get your estimate of what the initial conditions of the sample were, you do need to know something about how many parent and daughter atoms it would have contained originally. And the better you can estimate that, the better your dating will be.
What's the second thing we need to know about a sample?
You need to know whether something other than radioactive decay may have changed the ratios of the parents and daughters. This can happen, for example, if a sample is contaminated with something that could either add or subtract parents or daughters. This contamination could happen either at the time the sample was collected or at any point between when the object originated and when you're doing the measurement. For example, if you're collecting a sample from a piece of wood and you prick yourself on the wood and bleed all over it and the blood soaks in, the extra carbon-14 from your living blood will make the wood appear younger than it is. Or if you're testing a rock that's been sitting in a riverbed for centuries, the water that has seeped into it over all that time might have dissolved minerals in such a way that it introduced new parents or daughters, or it may have leached them out. And you need to take account for that somehow. In fact, I spoke to a geologist friend recently, and he indicated that you typically wouldn't use a river rock for radiometric dating for precisely this reason. But whatever you're testing, when you do your radiometric dating, you need to estimate how much contamination there may have been with the sample you've got. If the potential for contamination is low, your date is more likely to be accurate. If the potential for contamination is high, your date will be thrown off, making the sample either appear older or younger, and you need to correct for that.
And what's the third thing you need to know?
The radioactive decay rate of the parent atoms or their half-life. As we said in the case of carbon-14, that's been measured to be about 6,000 years, but it's different for every radioactive isotope.
How do we know what the decay rates are for different isotopes? We haven't been doing scientific measurements for 6,000 years.
No, but there are ways of figuring it out. First, you don't need to wait 6,000 years in the case of carbon-14. You can get a bunch of carbon-14 atoms and see how many of them decay into nitrogen in just a few days or months. You can then use how many of them decayed in that short period of time, and it'll be way less than half, but you can use that fraction to estimate how long it would take for half of them to become nitrogen. Second, you can do carbon-14 tests on objects with known ages, things that are thousands of years old, to see if the predicted decay rate holds up. As we mentioned last episode, scientists have done that for carbon-14 with ancient Egyptian artifacts whose dates we know, and also with samples from tree rings from really old trees that we can date. And the rate holds up. Third, you can predict what the decay rate of an isotope should be based on the laws of physics. Based on the number of protons and neutrons an atom contains, you can predict whether it will be radioactive or stable. And if it's radioactive, you can predict what it will decay into, and you can estimate how long it will take for that to happen or what its half-life is. This involves doing some math, but the principles for doing an estimate are well understood. They involve, among other things, the strong and weak nuclear forces and the various constants related to them. Thus, even before we discovered some of the recent elements, like oganesson, which is element 118, currently the highest one we've made, scientists were able to predict that it would have a really short half-life. And it does. An atom of oganesson 294 has a half-life of just 0.7 microseconds. And they were able to predict it's going to be in that range before they even made it. Scientists currently have predictions for elements that we're still trying to create, and they're already predicting that there may be a so-called island of stability coming up where the half-lives of new elements will be somewhat longer. Of course, once you've found an element, you'll want to do tests to confirm its half-life, and some of those have been really carefully checked out. For example, that's what enables us to make atomic bombs. To do that, you need to understand the half-lives of uranium and plutonium isotopes really well. If you use the wrong isotope or estimate its half-life wrong, your bomb will either fail to detonate or, worse, it will go off when you don't want it to.
Ugh.
Getting a really good handle on these half-lives was really crucial to the Manhattan Project back during World War II and to subsequent nuclear weapons research. You also need to know the half-lives really well if you want to build an atomic power plant. Get the half-life wrong and your power plant either won't make power or it will turn into a bomb and go boom. Finally, scientists have found that the half-lives of isotopes tend to fall along a certain line when you graph them, and we'll have a link to a table of nuclides so that you can see the pattern on the graph yourself. So there are multiple ways of estimating the half-life of an isotope, from predicting what it will be to directly measuring it in the lab, and you don't have to wait thousands of years for that.
But since we weren't doing measurements thousands or millions of years ago, these remain estimates, right?
Right, but they're really good estimates, and as long as the laws of physics are the same, so that the constants haven't changed, they should be valid.
Q, I've got a few people down on Rail 4 who are going to be hurt.
Yes. Your marvelous plan will not only tear the moon to pieces, but your precious ship as well.
You got a better idea?
Simple. Change the gravitational constant of the universe.
What?
Change the gravitational constant of the universe, thereby altering the mass of the asteroid.
Redefine gravity. And how am I supposed to do that?
You just do it!
Geordi is trying to say that changing the gravitational constant of the universe is beyond our capabilities.
Oh. Well, in that case, never mind.
Also, if the laws of physics have changed, there are ways we may be able to detect that. For example, there is some evidence that one of the constants in physics, known as the fine structure constant, or alpha, has not been entirely constant. Here's how Michael Brooks introduces alpha in his book, 13 Things That Don't Make Sense.
Alpha determines what happens every time a photon hits some piece of matter. Look at the wall opposite you. Whatever color you see because of alpha. A photon of light hits an atom in the paint. The atom absorbs the photon's energy and uses that energy to send out a photon that hits your eye. The energy of that photon determines the wavelength of the light it produces, in essence, what color you see. If the wall is orange, the photon has one energy. If it is violet, the energy is very slightly higher. It is still only equivalent to the energy in a billionth of a raisin. To work out what color you'll see from a particular paint, you need to do a calculation that invokes alpha and the quantum structure of the atoms and molecules. Alpha's significance is due to the fact that it is the most important constant in one of our most important theories of physics, quantum electrodynamics, or QED. This governs any and every interaction between the charged subatomic particles, the protons and electrons. QED brings together quantum theory, relativity, electricity, and magnetism to describe the origins of electromagnetism. Alpha is also linked, via the electroweak theory, to the weak force that gives rise to phenomena such as radioactive decay in atomic nuclei. Since electromagnetism and the weak force are two of the four fundamental forces of nature, it is fair to say that alpha plays a pivotal role in the universe.
And for reference, alpha is a fraction that's approximately equal to 1/137th, or 1 over the number 137. That's about 0.73%, or 0.75%. And alpha is one of those finely tuned constants that can't change much without wrecking the universe.
Tweak alpha too far, and small atomic nuclei, those of helium for example, would blow apart as the protons repelled each other. Stars wouldn't shine. Grow alpha by 4% and the stars wouldn't have ever produced carbon, and thus we wouldn't exist.
But there is evidence that alpha has changed within the range that doesn't wreck the universe. A number of years ago, physicist John Webb and his colleague, cosmologist John Barrow, looked into the question.
If you want to check whether something has been the same for a long time, you need a sample that's as old as possible. Webb and Barrow quickly realized they had access to a perfect sample, the light emitted 12 billion years ago by quasars, the hearts of young galaxies. The emission of light from a star involves a constant that is officially known as the fine structure constant, but is more often referred to as alpha. The quasar light would depend on alpha as it was 12 billion years ago, so analyzing that light would provide the best possible chance. By 1999, John Webb had what looked like an answer. The photons of light that carried his answer had traveled 12 billion light-years across the cosmos and landed on Earth in Hawaii at the Keck Observatory that sits on the summit of Mauna Kea. But what was most interesting about the light arriving at the Keck telescope was the light that didn't arrive. Webb and his team spread the light out into a spectrum. There were gaps in Webb's spectrum. His rainbow had missing colors. That wasn't interesting in itself. On a 12 billion year journey through space, you'd expect the light to encounter some matter. Clouds of gas are the usual culprits that absorbs light of particular wavelengths. This leaves breaks in certain parts of the spectrum, as if a decorator has left a few vertical white stripes in the middle of your orange bedroom wall. The interesting part of Webb's discovery was that the breaks were in the wrong place. Every atom, whether it's in an interstellar gas cloud or on the sole of your foot, will only absorb photons of particular energies. The energies in question differ for each atom. It is something like the atomic version of a fingerprint. As a result, by looking at the spectrum of light and what is missing from it, you can fairly easily work out what atoms the light encountered. The fingerprints in Webb's spectrum corresponded to two atomic encounters. One involved absorption by magnesium atoms, the other by iron. It was clear from Webb's spectrum that the quasar's light had passed through clouds of magnesium and iron on its trip to Earth. But there was a problem. Although it was unmistakable which of the well-known absorptions the gaps in the spectrum were meant to correspond to, they were slightly out of place, as if someone had nudged the spectrum. For some, the absorption lines were nudged slightly to the left. For others, they were shifted a little to the right. Webb sat down and redid the calculation. All the shifted lines made sense if he made one little adjustment. All he had to do was allow that when the light was racing through the interstellar dust clouds, the fine structure constant was very slightly different from what it is today. It sounds like a straightforward conclusion, but it took some guts to go public with the suggestion. Webb has been attacked for this. People, as he politely puts it, have, quote, questioned his sanity, end quote, in remarking that a constant of nature might change over time, especially one as central to physics as alpha.
But then more evidence came in that alpha may have changed. In 1972, scientists were studying a site at Oklo in the nation of Gabon in Central Africa, and they found an ancient natural nuclear reactor. I've previously promised to tell you the story of the Oklo nuclear reactor, and this is a good time for it.
Well, what was the Oklo nuclear reactor?
According to the standard scientific account, the Oklo reactor existed about 2 billion years ago. At the time, there were deposits in the soil there that had a lot of uranium-235, which is the kind of uranium you want to make a nuclear bomb or a nuclear power plant. As it decays, uranium-235 releases a neutron, and most of the time, that neutron goes whizzing off without causing anything interesting to happen. This is especially the case if it's a fast neutron that goes whizzing off at its normal speed. But some things, like water, can slow a neutron down, and if that happens, it increases the chance that the neutron will interact with another nearby uranium-235 atom. And guess what? There was also groundwater around the Oklo uranium-235 deposits, and the water slowed the neutrons down and increased the chances that they would interact with other nearby uranium atoms. When they did, that would cause these atoms to become unstable and release more neutrons, setting up a chain reaction. just like in a nuclear bomb or a nuclear power plant. The key difference between a bomb and a power plant is whether you let the chain reaction go uncontrolled, in which case you have an explosion, or whether there is something to control it, in which case it just generates heat for you. Well, in this case, there was something to control the chain reaction at Oklo, and once again, it was the water. The chain reaction of the uranium atoms would generate heat, and that would raise the temperature of the water, which then boiled off. Without the water, the neutrons became fast again, and the chain reaction stopped. But eventually, new water would seep into the ground, the neutrons would become slow, and the chain reaction would start up again. And presto, an entirely natural nuclear fission reactor. According to the standard scientific account, this cycle of on-again, off-again chain reactions went on for hundreds of thousands of years, until enough of the uranium-235 had decayed that there wasn't enough left to sustain a chain reaction, and the nuclear reactor shut down permanently. Now, here's the thing. The constant alpha was involved with the nuclear reactions that were going on at Oklo. And since the site is supposed to be 2 billion years old, you could check whether alpha had the same value back then as it does today. Back to Michael Brooks.
To science, the discovery is a gold mine. 2 billion years ago, the constant we call alpha was presiding over the precise mechanics of the nuclear reactions that took place in the ground at Oklo. If you want to know whether alpha really is constant, Oklo provides the best test samples this side of Alpha Centauri. The physicist Freeman Dyson was one of the first to jump on Perrin's find. Dyson, who has a reputation of being something of a rebel, had already been wondering whether constants and laws were really so unchanging. The Oklo reactor gave him a chance to find out. He enlisted the help of the French nuclear physicist Thibaut Damour and set about the analysis. Their conclusion was probably disappointing to Dyson. If alpha had changed at all, it was by no more than a billionth of its present value. When Webb's results came out, Dyson and Damour's Oklo data allowed most scientists to ignore him. Oklo contradicted Webb's findings and was much more reliable than an investigation of ancient starlight. Eventually, though, as Webb's findings refused to go away, a few people did start to look more closely at what Dyson and Damour had done, and they began to find flaws. There was no firm rebuttal of the Oklo evidence until 2004, but when it came, it was more than a rebuttal. It came down firmly in support of a varying alpha. The conclusion? Alpha has decreased by more than 45 parts in a billion since the Oklo reactor burned itself out.
45 parts in a billion is not a very big change in alpha, and that's good. You can't change alpha very much without wrecking the universe. Also, this is controversial, and not everybody in mainstream science accepts the idea that alpha has changed. But what it does show is that people in mainstream science are willing to consider that the laws of nature may have changed over time. It also shows that there are ways we can check to see if they've changed, and if so, by how much. That's the key point you need to remember, because whether the constants in nature change is going to be a big issue in what we have to say going forward.
All right, Jimmy, as we have reached the conclusion of our second part of this exploration of the young Earth, what is your next preliminary bottom line?
My preliminary bottom line is as follows. As we saw last episode, the sources of faith don't settle the young Earth, old Earth issue one way or the other, so we need to look at what the scientific evidence says. People of both schools of thought agree that the world's history involves a mix of uniformitarianism and catastrophism. There have been big catastrophes in Earth's past, and between those catastrophes, there are processes that operate in a slow, uniform manner. Sometimes there are things like catastrophic volcanic explosions or catastrophic mud flows that can create new layers or carve through them really rapidly. But we can't generalize from that to the idea that all mountains and canyons we see on Earth were created rapidly in the last few thousand years. What we need to do is find a way to directly date rock strata, and radiometric dating is one of the best ways to do that. But there are issues we need to be aware of with radiometric dating. We need to be able to estimate the initial conditions of a sample of material, that is, how many parent and daughter atoms it originally contained. We need to be able to estimate what kind of contamination it may have experienced in its history, and we need to be able to estimate the rate of radioactive decay for the atoms in the sample. We currently have really good estimates for the rates of radioactive decay, but these rates would be different in the past if the constants of nature had changed significantly. Fortunately, we have ways of detecting whether constants have changed over time, and we have evidence that some of the constants, like alpha, may have changed at least slightly. The question we need to answer is whether the rate of radioactive decay has changed enough to point to a young Earth.
All right. So that brings us to the finale, which we'll cover next time. But first, Jimmy, what are some...
The explosive finale.
The explosive finale. So what are the further resources we'd like to offer the listener today?
We'll have a link to Michael Brooks's book, 13 Things That Don't Make Sense, which is a really fun read, and it contains the story of Alpha and the Oklo nuclear reactor. Also, the websites for the Institute for Creation Research, the Creation and Earth History Museum here in California, articles on radiometric dating and radiocarbon dating, articles on uniformitarianism and catastrophism, as well as creation science, young Earth creationism, and the age of the Earth. We'll also have a link to that companion piece, the creation science publication, 100 Evidences for a Young Age of the Earth and the Universe, together with the responses from the folks at Rational Wiki. We'll have a link to that video, what actually happened at Mount St. Helens, as well as Dr. Snelling's Young Earth presentation on radiometric dating, a link to the table of nuclides that we mentioned so you can see the curve of how, depending on what element you're talking about, how long it's going to take it to decay. Also, an article on alpha, a short video on the Oklo nuclear reactor so you can see with diagrams how it would have worked. Also, pieces on natural nuclear reactors and time variation of physical constants in physics.
Excellent. That's some good reading. All right, Jimmy, let's consider some mysterious feedback from our listeners. This time we're getting feedback on our Ruby Ridge episode. Dan on Facebook writes, "Was that another Reno operation? Brutal story."
And when Dan posted this on Facebook, you had already answered it before I had to. So why don't you answer the question for once?
Sure. So I let Dan know, because I remembered from when we were talking about Waco, that Janet Reno wasn't nominated to become Attorney General until the following February. So this is not something that can be laid on her doorstep in this case. I don't know who the previous Attorney General was to Janet Reno.
Yeah, I'd have to look it up.
Yeah,
but it's not at the top of my memory. So Reno does get blame for Waco, but not for Ruby Ridge.
That's right. Marty from Queens writes via email, "Qualified immunity mostly protects me from being personally sued. As a cop, when I'm sued, I have to prove to the city that I was acting in good faith for them to indemnify me. If we stop qualified immunity, we should stop it for all government workers. Judges, politicians, presidents who drone American citizens. Janet Reno was mentioned, yet there was no mention of her being sued or arrested personally. Hospitals kill 250,000 people each year by mistakes, negligence, and accident on split-second decisions. How many doctors or nurses have been indicted this year? Sure, they can be sued, but they carry high insurance and get to charge more because of said insurance. Who will pay my malpractice insurance? Qualified immunity for all government workers or none for all. Let's be fair."
And I think Marty has a good point here, and I agree with him. Marty is one of a couple of law enforcement officers who've contacted me about qualified immunity, and I very much appreciate their feedback. I understand why qualified immunity is important to them. For people who may not remember, qualified immunity is a legal doctrine that was created by judges. It's not actually written into the law. Lawmakers did not ever vote on this. but judges came up with this doctrine to shield various people working for the government from being civilly prosecuted for wrongdoing. So if some government person makes a horrible abuse of office against you, you cannot sue them to get damages. And they may be held accountable, as Marty says, in the criminal courts, and they may have to, justify their actions at commissions of inquiry and things like that. But you personally, let's say they kill your spouse, or your child, you personally can't sue for damages.
Can't sue the individual, right?
Can't sue the individual, right. And so there is a question about should this kind of shielding exist? And everybody else in society is not protected in this way. So if you're, for example, a doctor, you don't have qualified immunity. And if you grossly do something wrong medically as part of your job, you can be sued for that. And people can get damages for you, which is why doctors have malpractice insurance. Same thing if you're a lawyer. If you're a lawyer, you don't have qualified immunity. And if you do something grossly wrong, you could be sued. If you are a bakery worker or an apologist or a podcaster or any job you want that's not a government agent, you can be sued personally if you do something grossly wrong. So other people in society do not have this protection. And although I'm open to arguments that there should be some form of protection for government officials, I'm not convinced by it. My instinct is to say they should not be shielded any more than other people in society. Now, because police officers, for example, are engaged in a dangerous and very valuable form of work, but one where they could be sued, they would likely need to carry something like malpractice insurance, just like doctors do. We have found a solution for doctors to enable them to do their very important but also risky jobs. Financially, we found a way to make that work to where they are individually accountable if they grossly do something wrong, but we have ways with malpractice insurance of handling that. And I suspect a very similar solution would be found for law enforcement officers as well as other government officials, especially those who involve risky things. And since their income is derived from the taxpayer, ultimately, I think the taxpayer, one way or another, would end up, either directly or indirectly, would end up paying for their malpractice insurance. And I acknowledge that they would need to have that, just like doctors do, at least in a type of job where you have these very risky things. But it also would provide a form of individual accountability that does exist for everybody else in society. And it would then exist for them too, just like it does for doctors and everybody else. I agree with Marty. If some government officials don't have qualified immunity, then others shouldn't either. It shouldn't be just a police thing. It should be across the board. And the American people should be able to individually hold government officials accountable for abuse of office in this way.
All right. Adam Hovey commented on YouTube, "The Christian identity movement sounds a lot like British Israelism. By the way, I am a full-blooded mutt, and my grandmother was active in the Pan-Indian movement. White, red, yellow, black, and everything in between, and every mix thereof, all the children of one God."
Amen. And you're right. The Christian identity movement is linked historically to the British Israelite movement. The British Israelite movement, which I'm sure we'll talk about in the future, and we actually talked about it a little bit in our episode on the Lost Tribes, believes that the lost tribes of Israel ended up becoming, or some of them ended up becoming, the inhabitants of Britain. And they have some really fanciful arguments for that, like even the word British. They'll try to say, ooh, that comes from Hebrew. Beret, meaning covenant, and Ish, meaning man. So it's a covenant man. And that's just totally fanciful. That's not where the word British comes from.
Okay. I
would say, though, not everybody who's a British Israelite is a Christian identity person, though.
Right.
So you have people who just have this view about where British people came from that is not supported by the historical evidence, but that doesn't mean they're, neo-Nazis or anything.
Okay. Ma'al Siklan on YouTube writes, a great episode. I'd never heard of this incident. Will you be covering the Jonestown Massacre?
Yes, we will be covering the Jonestown Massacre. I have several books and accounts of it that I've read, and it's definitely on the list, and it's got some weird stuff, including an account from a survivor who was not a member of the group, but who was there when it happened, who's also written extensively on the Kennedy assassination and happened to be there at Jonestown when everything went down.
Wow.
And escaped by hiking through the jungle.
Okay. So, Jimmy, that's the end of our mysterious feedback. What do we have for mysterious headlines?
Well, okay, we talked about catastrophism in this episode and how some catastrophes here on Earth may have been caused by supernovas. Well, we'll have a link to an article about how a supernova may have caused a mass extinction here on Earth 359 million years ago. So this is before the age of the dinosaurs, but nevertheless, a big extinction event may have happened because we got hit by radiation from a supernova. Also, speaking of stars going boom, our neighbor Betelgeuse, which is basically a bomb waiting to go off in space, has been dimming lately. And there's a bit of a discussion about, does that mean it's near the end of its life or not? Because we would expect it to dim somewhat in the final stages before exploding. Fortunately, Betelgeuse is far away from us enough that it won't hurt us here on Earth, but it would be spectacular, and I'd love to see it, assuming it doesn't wipe out any other civilizations in the process. But we'll have a link to that. And also, we mentioned that there's that alternate theory that Earth may have had its water when it formed, that it wasn't brought here by comets. That story's been in the news recently. There have been some studies of meteorites that people have used to argue that Earth already had its water, and so we'll have a link to that.
All right. So that's it from us on this time through. We're talking about the Young Earth 30. So what did you think? What are your theories about the scientific arguments we've covered so far on Young Earth? You can let us know online by visiting sqpn.com or the Jimmy Akin's Mysterious World Facebook page, or by sending an email to mysterious@sqpn.com, or sending a tweet to @MYS_world with the hashtag of mysterious feedback. So, Jimmy, what's our next episode going to be about?
Next episode, we'll be looking at whether the constants of the universe have changed in a way that points towards a young Earth, or whether they point to an old one, particularly when it comes to radiometric dating and the problem of distant starlight.
Very good. All right, folks, be sure to check out the Mysterious World bookstore at mysteriousworldstore.com for links to all the books and videos that Jimmy mentions in every episode of the show, practically. Some great reading there. You'll find links to Jimmy's resources from this discussion and links to those mysterious headlines on our show notes at sqpn.com/mysterious. And remember, to help us continue to produce the podcast and to reach our goal of financial stability, please visit sqpn.com/give. Until next time, Jimmy Akin, thank you for exploring with us our mysterious world.
Thanks, Dom.
And once again, I'm Dom Bettinelli. Thank you for listening to Jimmy Akin's Mysterious World on StarQuest.